In lecture 1, we got introduced to kinematics, right? And we talked about what is the concept of distance, what is the concept of displacement, what's the concept of either rest or motion, state, and we came across those important definitions. Then we wanted to know what is the uniform motion, what is accelerated motion, those things we discussed as a part of introduction. In this lecture, we are going to talk about, we'll expand our discussion to the displacement in vector terms, right? In vector notations, how we are going to express what it actually means, and then what do we mean by position vector, extremely important concept. So I have made this frame of reference, and we are here in this frame of reference, and we imagine ourselves in space. So we have y-axis in this direction, we have x-axis in this direction, which is protruding out towards you. So this is the xy plane, and on the xy plane we have z-axis coming out of the plane xy. So this is essentially zy axis, this is xy axis plane, and this will be zx axis. So imagine this three-dimensional coordinate system on two-dimensional projection that is on the board. All the three axes are mutually perpendicular. So now we try to find out what is going to be the displacement in terms of if we know the coordinates and if we know the position vectors. So what exactly is position vector? This is located in space A point, initial, and the final is B point, it's located in the space. And we want to know that what is the change in this position, that is what is the displacement of A when it reaches to B. So AB basically is showing you the displacement vector. And we have a location of A as XA, YA, ZA. These are corresponding coordinates in this XY. So this XA means if we have taken X in this axis, so this XA means this distance along this x-axis. So this is the A, and we want this. So this is lying at what distance from this origin? Okay, so this distance XA is shown here, XA. Then we want to know that this has a coordinate Y, so which one exactly it is showing the distance from the origin. So this Y, along this Y axis, we have this as Y from origin to this position, initial position, which is YA. So YA is this, and what is this height, which is it is raised up to this height ZA from the origin to this point, and this is shown as ZA. So this is a three-dimensional, you need to imagine that. We have now XA, YA, ZA as an initial position. Then we have here XB, YB, ZB as final position. So we can write it here. This is the initial position. And this is final position. Okay, so the coordinate of B is XB, YB, ZB. So if you drop a projection here, this is going to show you on the XY plane again, the same thing. So this distance from the x-axis, this is showing you XB, this distance. And this is showing you YB. And the one which is going up above the XY plane, that is the height, which is ZB along the Z-axis. These two are parallel. That is how we imagine these projections there. Well, the position vector means this initial and the final in this space. If we draw a vector from the origin pointing to the initial position, and we denote this by R vector, R with a subscript A vector is the position vector of point A, which is the initial position. And for B, RB is the position vector from origin. We draw a vector pointing towards B, and we use this notation RB vector showing in which direction it is. So now we are interested in what is this S, displacement from A to B. In vector notation, how we are going to write, and we also know that unit vector along x-axis is I cap, unit vector along y-axis is j cap, and the unit vector along z-axis is k cap. Having this understanding, now let's write this in terms of vector notation. So if you want to project this RA, how can you write RA? This RA in terms of unit vector notation, it could be written as XA I cap, the magnitude multiplied by I cap, plus YA J cap, plus ZA K cap. Similarly, RB vector could be written as, in vector notation, it would be XB I cap plus YB J cap plus ZB K cap. Now these are those coordinate systems that we have there. Now we want to figure it out in terms of this, right? RA vector, XB vector, and this. So if you want to find what is this position vector, that is, you want to find what is AB, actually you want to find what is S in terms of those. So we know that this, if you apply here by triangle law, we can write by triangular law, vector triangle law, we can have a relation RA vector, so this vector plus the displacement vector should be equal to RB vector. All right, so if you want to find what is S vector, you can write it as RB vector minus RA vector. So RB we already know, this is RB, RA we already know R, so we can get here an expression. We can write S vector is equal to, RB could be written as XB I cap plus YB J cap plus ZB K cap minus RA vector is XA I cap plus YA J cap plus ZA K cap. Okay, so now if you subtract this, therefore we get S as, so if you open the bracket, it's going to be minus here. This also will be minus, this also will be minus here. You take I cap common, so it's going to be XB minus XA I cap plus YB minus YA J cap plus ZB minus ZA K cap. So this is what we get in vector notation, the displacement vector. So S is the displacement vector. So suppose if I draw a path here and I want to show the difference between distance and displacement that we discussed in the last class. If we want to show it here, suppose this is the actual path, okay? So if you want to find the distance, you are going to calculate this actual path length. However, the displacement is going to be S. And this is going to be RB vector minus RA vector, which is the shortest path. So this is showing you this displacement basically. What is this? The shortest path. That is displacement, and the displacement vector in terms of unit vector notation, we have that expression. So you can take this down, and after this we are going to talk about what is we'll talk about here what is average velocity, and then we'll talk about what is instantaneous velocity. So take down these steps as a reference point, and from here we'll move on to average velocity and average speed concepts. So to understand about average speed and average velocity, we'll imagine that you are going on a bike, and at times you slow down, at times you speed up. So if you want to plot your position with respect to time, then we'll get a graph. So we'll understand from graph plotting what is the basic difference between these two quantities. So suppose if I want to plot a graph, I would be getting this if you have time axis here and you have position. So this is a position time graph. Showing that at times you accelerate quickly, at times you slow down abruptly, and if you want to trace the positions, different positions, and you want to find what is the time here, then you need to connect all those points and we'll be getting the curved nature of it. And suppose at any instant of time here, if I want to show that this is suppose one position in the path and this is another. Suppose this is here x2 and this is x1. Correspondingly, this is t1 and corresponding time for the other position. So this is suppose A and this is suppose B. So the time here is going to be t2, suppose. Well, and this is the path here. This is actual path that you have got, that you have traced as moving along the time. You take down the positions that you have been displaced, and then when you plot, you get a curve, because that's what the situation was. So from here, if you want to find what is the average, so we know that if you join these 2 points, A and B, this is going to show you what is the change in the position. So if you want to see what is the change, so this is x2, this is x1, so this is x2 minus x1, which is delta x. And during this from A to B, this journey, what is the time interval? So the time here is t2, the time here is t1. So this is this difference is t2 minus t1. So that is what we call time interval, delta t. So if you want to find what is the average velocity, so let us denote that this is average velocity. So this is going to be x2 minus x1 over t2 minus t1, or we can abbreviate this as delta x over delta t. So this is going to be your average velocity, which is giving you a sense that a change is happening during this time interval, the change in the position, and that is what the displacement means, the change in the position. So x2 minus x1 over t2 minus t1 is going to be the average velocity of your journey from A to B if you have this kind of plotting done. Well, having understood this, then what is average speed? If you take the actual length, then we will find average speed. So average speed is defined as actual path length, or the distance, actual path length. And this is what we call distance. So distance over the time interval. So this is what is average speed, and this by definition we have a quantity, very important quantity, average velocity. So take down these small bit of understanding on the how we relate the positions and how we get the formula. So take down these two equations. Now a question comes, if this is the average velocity, okay, however, if I want to find at any instant of time, if I want to find what is your speed or what is your velocity at any instant of time, this average is not giving you a sense of instant. It's giving you over a period of time. You have slowed down, you have accelerated. So over the period of time, this is what the average comes out to be, the velocity. However, at particular instant, what exactly was the speed or what was that velocity? Where was it? So that instant concept is where we want to move from here to have an example showing that why we want this instant that is quite real in real world, and above all, how will we get that instant velocity from the graph. So let's plot another graph and let's take some actual values to understand this. Here we have the position time graph and we have taken the time in seconds. That is how we have listed the times here on the x-axis, which is the time axis, and correspondingly we have here the positions. So it is taken in meters this way and the time is increasing in this way. Okay, so we want to go from A to B here. And we have already seen it's going to give you the average velocity. And so basically in this curve, this is actually a secant. Right? So 2 points in the curve, if it is joined, and this point which joins these 2 points on the curve, we call this in mathematical notation, we call it a secant. Well, now this is what the situation is. The situation says that suppose we take 4 seconds as our starting point, which corresponds to, at any instant of time, we have taken 4 seconds as our point A. And we want to find at this point, at 4 seconds, we want to find at 4 seconds, what is the velocity. So that is what we want to find. What is the velocity, which is the average velocity at this point, at this point. Okay. At this point, what's the velocity? And how we are going to find? Let's see the quite interesting part of it. So if you take this into account, suppose if you take and observe this pattern, what is the time interval between 6 and 4? So we get here delta time t is equal to 2 seconds, right? So if you take t is equal to 2 seconds, now corresponding to this, so this corresponds to 16. And this corresponds to 5, right? So this corresponds to 16 and this corresponds to 5. So if you want to find the average velocity is AB is 16 minus 5 over delta time t is equal to 2. So it comes out to be 11 by 2, which is 5.5 meter per second. You agree? All right. You agree with this? Well, now if you find, suppose if you shrink this time interval, it was 2 seconds. Now if you want to shrink the time interval, suppose we take from 4 and we take 5.5. Suppose we take this. So here we'll have delta t as 1 second. If this is so, what's going to be the average velocity? So 5.5 minus 4 is 1.5, right? 1 second. So we want 1 second. So let's take 5 then. Let's take 5 here. If you want to take 1 second, so it is 5. Now 5 corresponds to 8 and 4 corresponds to 5. So it is 5 minus 8 minus 5. 8 minus 5, which is 3. And what is the time, which is 1. So it comes out to be 3 meters per second. So if you want to find at this instant of time here, at this point, which is suppose A, B, C if I take, and I want to find, now this point B has moved to this point. So now it has become in this way. And now we want to find this. Corresponding to this, we get 8 and minus 5, which is 3. And this divided by 1. So average velocity AC, it comes out to be 8 minus 5 over 1, which is 3 meter per second. All right. Now if you want to take suppose 4.5 and you want to take this interval, that is 4.5 corresponds to 6 and 4 corresponds to 5. So it is coming out to B. So now if you want to move this C, and the B has moved to C, now C has moved to D, suppose, and now you want to find this particular interval. So if you want to find the average velocity, AD, this comes out to be 6 minus 5 divided by, here it is 6 minus 5. So 6 corresponds to 4.5. This corresponds to 4. So 4.5 minus 4. This comes out to be 0.5, which is 1 divided by 5, right, into 10. So this comes out to be 2 meters per second. Now you find something interesting. The interesting part is the average velocity is decreasing. The average velocity is decreasing, and as it is decreasing, we see the time as it is shrinking. It is coming closer to this point. So the average is actually coming to A, approaching A. So initially it was at B on the curve, now it is at C, now it is at D. So if I'm going to shrink this time interval, I find that this B finally approaches A, and then we'll be able to figure out what is that instant. At this instant, we'll be getting that value of the average velocity. Now at A point, if this secant is moving, right, that secant was at B, now it has moved to C, now it has moved to D, now again it's going to move, which is quite near to this. You would find that it's becoming a tangent. The secant would become a tangent. So we find that this pattern shows that as delta t approaches 0, right? So it was initially 2 seconds, then we made it 1 second, now we made it 0.5 seconds, right? If we are going to shrink it, so what exactly it's going to be as it is approaching, that is how it is defined. So if you want to mathematically understand this, if you take the limit of the average velocity, where you shrink the time to 0, as the delta time t, the interval is approaching to 0, this is what is instantaneous velocity, and this is what we call dx by dt. That is what we call, when delta t tends to 0, that is, this interval becomes infinitesimal small. Then where this average is going out to be the average velocity, the limit that we take the average, because it's in the denominator, right? It cannot be 0. So if we take a limit for a finite value to be there, so the limit of average velocity when the delta time t tends to 0 is what is the derivative of x differentiating x with respect to time. That is what the notation is. And this is actually giving you instantaneous velocity. This is giving you instantaneous velocity. Instantaneous velocity. We have started from 4 seconds here. So delta time, as it is approaching 0, this is going to be at 4. So the average velocity at 4 is actually limit of dx by dt, which is the average velocity limit taken when t tends to 0. That is, we take the derivative of this x, which is position with respect to time, we get the instantaneous velocity. This is the concept of instantaneous velocity. So how can we define it? We can define that the instantaneous velocity of a body or of an object is the velocity at an instant when the limit of the average velocity is taken, when the delta time t, when the time interval becomes infinitely decimal small, we get instantaneous velocity. And mathematically, this is how we write it. It is dx over dt. So this is the concept of instantaneous velocity. We have understood average velocity, we have understood displacement, we have understood distance. Having known these things, we'll move forward with questions based on these quantities, how we relate and how we find the solution to the problem. So keep watching this video for your conceptual understanding.